and NUS, A-STAR, which is the Agency for Science and Technology Research in Singapore, and some collaboration with Abu Dhabi for our qubit controls, and Professor Ali Bosbey in Ankara. So this is the rough outline of my talk. So I will give a brief introduction of superconducting qubits, and then we'll try to list the requirements and challenges of trying to build a good superconducting processor. So this includes from the beginning how we design our qubits, need to simulate them, the fabrication process, and then the characterization and control. And then we will go about the superconducting qubits on quantum technology in Singapore and elsewhere. And if we want to build a fault-tolerant quantum computer, we need more things to be done, and there are a lot more challenges to be used. So why superconducting qubits? I think in the morning, Dr. Gal just gave some of the pros, so high fast gates and good gate fidelities. And another thing is that ideally we want a quantum state that is within a log, it should be at ground state. So there are reset schemes to make the qubits to start in the ground state, but at cold temperatures, just by Boltzmann distribution, it should have a low excited state population at equilibrium. Another advantage is that we fabricate it, so in a sense we can control what kind of frequency, what kind of gates, what kind of coupling schemes we want. And we can fabricate this native nonlinear element, which is called Josephson junctions. And basically, all superconducting qubits use what's called Josephson junctions, which I will tell in the next slide here. So basically, Josephson junction was first found by Brian Josephson back in the 1970s. So in principle, it's 2 layers of superconductor separated by thin separated by a thin layer of insulator, the red line in the middle. It's insulator. People actually try different things. For example, normal metals are like very narrow superconducting channels, but the most common one is an insulator. So what Josephson found was that this current and voltage follows what's called the Josephson equations. So the current so the phase across the Josephson junction, this is the depends on the current and the voltage, and the voltage actually depends on the change of the phase over time, and the current has a sinusoidal relation. So if you work through the equation, you can find that effectively Josephson junction can act as a nonlinear encounter. So it has V as a function of the IDP, but this proportionality constant also depends on the phase, which depends on the current. And here, there is something called the flux quantum that will show up a few times later, h over 2e. This is actually quantization in superconducting Josephson junction. This term appears a lot. So, another thing that I need to mention is that if we have 2 Josephson junctions and put them in parallel, and you create this closed loop, we have something that's called DC squid. So here the magnetic flux inside the squid needs to be integer multiples of this flux quantum. So if we apply a magnetic field such that the magnetic flux is not integer multiple of flux quantum, there will be circulating current to counteract this such that the magnetic flux will actually always be it's not integer multiple of flux quantum. So this actually causes the effective critical current. So this, if you consider this as a single Josephson junction, the effective critical current depends on flux. And this is used on some superconducting qubits to basically tune the critical current and tune the frequency. So I will roughly these days, the superconducting qubits comes with in these two families. So what's called a flux qubit. So effectively, the circulating current would be going clockwise or counterclockwise. And the second one would be what's called charge qubit. So effectively, because we have this two superconductors separated by an insulator, this actually acts as a capacitor also. So okay, I didn't define Cooper pair. That's basically the charge carrier in superconductors, and basically the quantum state depends on like how many Cooper pairs are stored in the junction. I mentioned here, so that's kind of like the initial version of it. Now there is basically more modern version. So for flux qubit, it's called Cesium flux qubits. There is also something called fluxonium. For the charge qubit, the most commonly used in basically everywhere is called transmons. And I think somehow the superconducting qubit people like to name their qubit strangely. So there is also something called quantronium, G1, X1, maybe someone wants to name it Pokemon, but they are not like Nintendo shoe or something. I was thinking maybe if I have you design would want to name it like that, but yeah. So, okay, so let's start with basic of like the superconducting structure. So the most simplest structure that you can think of like would be a quantum harmonic oscillator, and you can create this in a circuit by creating a capacitor and an inductor. And then if you solve this equation like the Kirchhoff's law, you can find that this oscillating frequency is just 1 over square root of LC. And if you solve this quantum mechanically, you have quantum harmonic oscillator with the same frequency. So you have this ladder with equally spaced. So this cannot be used as a qubit because if you start in a ground state and then you drive at such that the qubit goes to the first excited state, it can, and then if you drive further, it can go up to the higher levels. So for a qubit, ideally we want to isolate the two-level systems. If we cannot have that, we want to have a two-level system that we can somewhat isolate from other levels. So what we do is we replace, I mentioned earlier that the Josephson junction is a nonlinear inductor. And so we just replace the inductor with a Josephson junction. And the Hamiltonian basically changes to this one. Okay, I define here the EC is the charging energy. That's what people usually use in the superconducting community, but this is based here and is the number of the charge and the phase actually have commutation relation, so it's similar to position and momentum in say real space or yeah. And then the inductive element we have this what's called the Josephson energy, and instead of the standard Li squared, we have the cosine term as the inductive energy. And so for transmon, we usually work in the regime where EK is much larger than EC, and we can expand this cosine term up to the fourth order. For the second order, we basically have the same exact quantum harmonic oscillator frequency 1 over the square root of LC. But if we have this to the fourth order, we can, the ratio of EK over EC is much larger than 1. We can work out that the energy levels or between the energy difference between the lowest excited state and the first excited state is different between, compared to the first excited and second excited state. So the difference would be actually is EC, and so we can isolate use these lowest two levels as qubits. So I mentioned a little bit about some of the parameters. I will actually say the real values. Typically for a transmon, we want EK over EC of 50 or larger, and we use microwave to control the qubit. So I apologize somehow. So the energy here, I will always say it in frequency. So I'm actually doing the theorist way of H equals 1, but Because what pulses we send is all microwave pulses and we can control the frequency. So it's easier to take off everything in frequency. So the typical energy we use for the qubits, the lowest energy levels, the separation would be around 5 gigahertz. And we want this unharmonicity to be large enough so that we can send pulses, and typically for trans1 it's about 200 to 300 megahertz. If you calculate the capacitance, this is about 80 femtofarad. And then for the critical current, the EJ, it's usually about, that means if you calculate, it's about 14 gigahertz. So I mentioned earlier that the junction works as a capacitor, but this is actually a relatively small size. So the typical junctions we have, this is one of our old junctions, is about 200 by 300 nanometer. So if you try to calculate, say, parallel plate capacitor for aluminum oxide, and the typical thickness of aluminum would be around, say, 1 nanometer. Sorry, for the aluminum oxide, it would be 1 nanometer. The typical junction capacitance is 1 femtofarad. So we need basically another 80 femtofarad. So for trans1s, we require a shunt capacitor. So this is how trans1 qubits generally look like. All basically use a different kind of capacitor. So for the early trans1s, they use an dedicated capacitor. So you have two interlocking fingers together, and then this is what's called by as X1 because it's plus sign, but it's basically a trans1. So the capacitance would be, so the junction here is the middle here. For the X1, the junction would be like where I'm getting, and the capacitance would be between the center conductor and the ground. And then there is something, we can use this kind of pedal capacitor or like different shape of capacitor. So I mentioned earlier about the DC squid. So we can make the junction, a single junction junction, or a tunable junction, a DC squid. So then that means you have a fixed frequency qubit or a tunable frequency qubit. So for fixed frequency qubit, and this is kind of a choice that some different groups make. Some prefer tunable frequency, some prefer fixed frequency. So for fixed frequency qubit, once you fabricate them, you measure the resistance and everything. It's hard to change frequency. So tunable frequency, you can tune the frequency up to if it's slightly off to a desired range. However, this comes with a drawback that this superconducting loop has flux noise, and typically the coherence time of the qubit is basically how long the qubit can hold its coherence tends to be shorter, about 10 microseconds, while the best single junction qubit goes to 100 microseconds. Of course, that having tunability means you can have also like more flexible quantum protocol, so you can design some kind of algorithm or pulse sequence that utilizes this flux tuning. However, so that there are different trade-offs. How do we read out the qubit? So this is actually very similar. So if you've heard cavity QED in atomic systems, you basically have, if you have an atoms inside an optical cavity, you basically probe the atoms with due to the changes in the cavity response. So in our case, we usually use the same. So we use a resonator. So here we have an LC resonator, for example, and this will be coupled typically capacitively for trans1 to the qubit. So if we have this kind of coupled system, we have what's called the James-Cummings model. So we have the qubit Hamiltonian I showed before, the cavity Hamiltonian I showed before, and there is the interaction there. And typically for superconducting qubits, we operate, and so this interaction terms, there is a coupling term G. Typically, we operate in what's called a dispersive regime. So the distance of energy between the cavity and the qubit is much larger than the coupling. So this is because as a result of this dispersive regime, the qubit, when we probe cavity, the frequency of the cavity will depend on the qubit state. So I will simplify if for just a two-level system, if the frequency of the resonator is somewhere in the middle here, and the qubit is in the ground state, it will move to the right. And then when the qubit is in the excited state, it will move to the left. So we have to sit either on one of these states or in the middle and see the response. And by knowing how much it's supposed to shift, we know what the qubit, state of the qubit is. So this discrete shift for a two-level system is d squared over delta. So delta is the energy difference. For transmon, because we don't have just two-level systems, this will be more complicated, but it will be quite similar. So for the typical values, it's about delta is about 1 gigahertz and G is say about 100 megahertz. This is about the dispersive shift of about 10 megahertz. And again, there can be many different designs of the resonator. So I showed the resonator as this LC component. This is actually what the middle one looks like, because you have this meandering line of the inductor and this big fat acts as a capacitor. But most of the cavity that's actually being used doesn't actually look like this. So I showed this picture before for qubits. This is actually the cavity is 3D rectangular microcavity. So you can use this microcavity usually if you have a hole of about a few centimeters by a few centimeters. So using a superconducting quantum processor, we also need to couple qubits together. The easiest one would be we just couple two qubits together with a capacitive coupling. So we can use the same thing, fixed or tunable coupling. If it's fixed coupling, the easiest one would be just use a fixed capacitor here, for example. Or you can also use basically what's called a bus resonator, the coupling resonator. Or you can also use something basically an effective tunable coupler, which is basically an qubit. Again, so having a tunable coupler means you can effectively want to turn it on and off. So you only turn on the coupling when you want to kind of the qubits together. So for fixed coupler, you cannot easily turn it off. Typically, for fixed coupler, you require longer gates compared to the tunable coupler, and the same thing with the tunability, you have more flexibility. Yeah. So now I will switch here and go back to the beginning again. And basically, if we want to start designing a qubit, we want to simulate like have these qubits as at the right frequency, and the resonators at the right frequency. So what we usually do is we say use the finite element simulator, so ANSYS HFSS or console, and then simulate. So for example, this is one of the resonator structures, and we simulate the frequency, and we can check whether the electric field distribution makes sense as the mode of the rest of this resonator. And then we also need to find the coupling for this. We want to find a specific coupling between qubits or to the resonator. So we need to simulate also the coupling capacitances between qubit and cavity, qubit and qubit, and then say we need a control line to send microwave signals, and also between the cavity and the readout line to control the cavity. So once you have it, and then you will have something like this, for example. So this is one of our recent qubits, I guess. So the red squares are where the qubits are, and then the green squares are where the readout resonators are, and they are coupled to the readout line on the right. This is where we send the signal to go the cavity. And then the purple lines on the left is the qubit right line, where we send the signal to excite the qubit. And then the yellow is the bus resonator. And in our application, we usually have a lot of the best Josephson junctions. I will tell you why we didn't test the Josephson junctions and how, but we have a bunch of only single chip. So it will look a little bit like this. So this is something about 8-qubit chip. So the earlier one was just a cut of it, and then we need to draw this so that we can do the lithography process. In practice, because we use a CAD software to draw, and then the simulation is also, we can import CAD software, we just go back and forth to do that. So another thing is that, okay, there was Qiskit tutorial yesterday. One of the, I think, new options for Qiskit is called Qiskit Metal. I have not actually used it myself, but in principle, they can actually do this link between ANSYS HFSS, like element solver, and then like circuits model and design. So it can help in designing qubits. So we, for the fabrication, the scale of the resonators for like open wave lambda element is usually in the micron scale, and the junctions are in the nanometer scale. And basically, this purity and cleanliness is very important, so we need to fabricate in clean rooms. So in Singapore, we have a bunch of clean rooms at NTU and NUS, and also at A-Star. So these are the places where we tried fabricating. Most of the fabrication in this case is done at the Center for 2D Materials in NUS, and also at A-Star with IMP and IMRA, which are two different institutions that does a lot of applications. So I mentioned about the length scale, micron scale for the larger features and hundreds of nanometers for the smaller features. So that actually requires two different lithography processes with two different resolutions. So for the larger scale, we use something that's called photolithography. Typically, this uses about 400 nanometer light. So the typical resolution of the structures will be on the micron scale. But this would not be enough for the junction, and we use what's called an e-beam lithography. So instead of using basically photons, we use electron beam. And this, the wavelength, the resolution would depend on the wavelength of the electron. And typically, for this kind of 100 nanometer scale, it works. In principle, if you want, you can also do everything in e-beam lithography, but for 4-inch wafer patterns, that would, I assume, take too long. So this is why we have to split this process. So for the base of the chip, we typically use either sapphire, which is aluminum oxide, or high resistivity silicon wafer. So this is the rough process. So we start with the cleaning of the wafer, and then first we deposit the superconducting metal, and then do the lithography to pattern the area where we want it to be, etch the superconducting metal, clean it again. For the e-beam lithography, typically for silicon or sapphire, the typical superconducting metal like aluminum, you cannot actually see it. So the contrast is very bad. So typically we want to put another layer of metal that acts as a marker. We typically use gold. I think there are other options. So then we do this total lithography of gold, and then after we can do the EBL. Once that's done, there is one step missing, which is actually the most important one. After the EBL is the junction deposition. Once that's done, we can cut. So this is a 4-inch wafer, and this is there is a different 10 millimeter by 10 millimeter, so it's 1 centimeter wafer, 1 centimeter chips. We need to cut them to size, and then once that's done, it's ready for packaging. So I did mention we use superconducting metal for the resonators, and if you look at the literature, typically people use I think mostly these four different metal now. So aluminum, critical temperature is at 1 Kelvin, niobium at 9 Kelvin, titanium nitride at 5 Kelvin, and tantalum specifically you need to be with the alpha phase of tantalum at 4 Kelvin. And different groups will say like, okay, this metal is the best, and for the aluminum unit, a molecular BRIN epitaxy to have a good qubit. So far we have done use aluminum. We tried tantalum once and that doesn't seem to work so well. However, I think so. Talking with us, they can do in US a couple weeks ago. He came to March meeting ABS in the US this year, and basically 5 different groups presented this long coherence times transmon of 400 microsecond, and basically all use the different materials. So MIT uses aluminum, EPFL, which is in Lausanne in Europe, niobium. Again, in Japan use titanium nitride, and then IMEC in Belgium use tantalum, and Fermilab actually uses a combination of this tantalum and niobium. So it seems there might not be difference in terms of like superconducting material. So most likely the issue would be on the cleanliness, on the issue with the interface. So what does this mean? So it has been known that this what's called the two-level systems is a major source of qubit loss. And typically, they are thought to be like defects on the surface or dangling bonds. So this can come from in the dielectric, and if we have a superconducting material out, they will measure like metal. Typically, they will measure form oxide. So this is true for all these form metals that I mentioned. But also there can be surface interface losses. So we have the substrate, and then the metal, and then the air, and then different layers of metal deposition. So there can be metal substrate interface losses, metal to substrate to air, metal to air, and metal to metal. And this, in addition to from this oxide layer, they can count if your lithography is not clean, so you will have lithography resist remaining, or also developer to clean the resist. So proper surface treatment and cleaning is important, not just at the beginning, but also during every steps. So I will cover a bit about the fabrication of the Gaussian junction. Typically, everyone uses the aluminum oxide, aluminum junction. It's the most established one. So what we do is we do 2 aluminum deposition. Typically, we use something called e-beam evaporator, but separated by an oxidation in between. So we need this specific value of the critical current, so we can control this by how long and what's the pressure of the oxidation. So so this is kind of like the rough illustration. So what we do is we do the e-beam lithography to determine the pattern, and then we deposit the first aluminum at an angle, and then do the oxidation step in between, and then do another layer of aluminum. So this is called the golden bridge. So we actually shift into a different junction fabrication model called an bridge, but in principle it's basically the same. So once we have this, and we have a bunch of junctions in the qubits, and we have a bunch of junctions in the best junctions, we can estimate the critical current by measuring the resistance at room temperature. So there is this what's called the Rangga relation. So the critical current times the resistance is basically proportional to the superconducting gap. So for our case, and we want to measure as many of these qubit junction and test junction as possible to estimate the yield. This maybe during the process there are some issues and the junction can be shorted or actually open. But also we actually want this resistance, we say we want it to be 12 kilo ohm, for example. That gives us about this 30 nano and critical current. If we make them all to be 30 kilo ohm, 12 kilo ohm. So far we have within a single chip about 5 to 10% standard deviation, and within voltage wafer about 20%. The best values, I think, this is the report from MIT, about 2% within the chip and about 3 to 5% within the bio wafer. So it's something we need to improve. Once that's done, we put it in a packaging, do the wire bond, and then close it up, and then put it into the dilation bridge. So I think quite show the picture of the dilation bridge. So the idea is that we have this layers at different stages, and we put our experiment at these lowest stages at 10 millikelvin. Why we at 10 millikelvin? So one, because that's where all the metals are superconducting, but the most important one I mentioned at the beginning is that we want our qubit to be the ground state when we in equilibrium. So for a 5 gigahertz frequency, that gives, if you were out the energy over kT, energy over K, the effective temperature is about 200 milli, so we want something much lower than that. So we want at least lower than 50 milli. And then to send the signal, we actually have to send the signal going through this microwave line on the left, on the U square on the left, going from the top to the bottom. And this is kind of like the wiring diagram. So we have, on the input side, we need to have a bunch of attenuators to reduce the thermal noise. However, that results basically in a very small signal, so we need a bunch of amplifiers on the other side, and there is also isolators to prevent the signal from the other side going in. So for qubit experiments, we need to create probabilities. So we typically will average about a few thousand repetitions. However, depending on some applications, we need to have a single shot readout. Right now, we don't have that. We need to add what's called a parametric amplifier, or Gaussian parametric amplifier. This is basically typically using an array of Gaussian junction and use their nonlinearity to actually create an amplification. It's something we are working on, but we don't have that. The main thing, another thing on this slide is that we have control. We need to send microwave signal to drive the qubit and the cavity, and then need to split out the state of the cavity. So we have DAC and ADC. And for this one, we have what's called an FPGA, field programmable gate array board, for pulse generation and detection. So it looks like this. So I think this is a board from High-Tech Global, and there are some people in our group also collaboration with other people to make this as a wave generator and with the ADC. So it's the sampling rate is about, for the DAC, about 60 decibels per second, and ADC sampling rate is about 2 decibels per second. And if you know this kind of signal generation, actually the signal frequency is limited to half of the sampling rate. So if you want to send frequency at, say, 5 gigahertz, technically this is limited to about 3 gigahertz or 6 gigahertz sampling rate. However, there is also this effect of aliasing. So we actually have this shadow at the higher frequency range, and we actually use this at the higher NIQ zone and filter the lowest mode for our signal generation and detection. And we have this, we can do multi-channel and multi-reverse synchronization for large amount of qubits. So this one for 16 and 16 channel DAC and ADC, that works for about 8 qubits per about 16 qubits. So once we have those, we can characterize our qubits. I think the two typical characteristic time would be T1. So if we send the qubit into an excited state, and it will go react down to the ground state, that's T1. So and T2 would be the phase coherence. So our qubit lifetime, we typically get about 10 microseconds, even though we use a single junction, so fixed frequency qubits, so there's still more steps to be done. Another thing I want to mention is that there are fluctuations on this T1 and T2. So if you set this, measure this at the beginning, this T1 and T2 will drift over time. Also, the frequency will drift over time. And when we try to do the power spectral distribution of this frequency fluctuations, we found this 1/f equivalence. And we think this is due to the critical current fluctuations that have been reported of 1/f noise in critical current. And then once you have that, you can calibrate your single qubit gates. You can do single qubit gate randomized benchmarking. So you basically do random sets of single qubit gates and find the average fidelity of the single qubit gates. So right now we have about 99.8%, and it's actually limited by our qubit lifetime. So the other possible sources of this infidelity is also like from imperfect control, for example. Ideally, we want this to be as high as possible, 3 nines, 4 nines, even higher. Once we have this, then okay, we can continue on quantum state tomography, 2 qubit gates. We have tried CMAP gate, and but for our qubit chip, we want to do also a cross-resonance gate. So I think during lunch classes, and when people ask about like what do we want to do in Singapore, so this is a few slides on that. So we currently have this National Quantum Steering Committee, and basically all the quantum office, which is housed in A-Star. So my institution CQP is down here. And last year, they actually announced this 3 national quantum platforms housed in A-Star. The quantum computing hub, basically they want to create this kind of quantum applications called the industry collaborators. The quantum safe network is for quantum network security, and the fabless foundry is for microfabrication. Although I am confused, they are doing fabrication, but their name is fabless. So I'm not sure what the naming system is, but that's their name. So the idea is that basically CQP in collaboration with the NQCH and the National Superconducting Center, we want to put quantum computer in the cloud, ideally within a year. So this would still be an early stage, only about 10 to 20 qubits. And in the fridge, we will have control electronics that is ready for up to 40 qubits, so we can upgrade it later. So this corresponds to about 100 microequation lines and about 70 DC lines. And I think Dr. also showed the sycamore processor. So there has been other people are in the world. So Google and this is USDC China are ahead of us, and they show this quantum advantage or quantum supremacy. And for them, they both use tunable qubits and tunable buffer. And I need to update the IBM one because they just had this press release 2 days ago. So from 433 qubits, now Condor have 1,100 something qubits. And also Incan and Fujitsu announced earlier this year they have this 64 qubits. And this the IBM, we can use fixed qubits and fixed buffer. So, however, if we want to scale up to more qubits. So to have fault tolerant quantum computing, we need about 1,000 qubits that are very good. Right now, even with the best coherence times, that's not what we have. So we need basically use this error correction code. So for example, something called surface code or bit and short code. Basically, you use few hundred or few thousand qubits as a logical qubit, and then you need 1,000 of this to actually to be used for quantum computation. So you need millions. So that's a lot more than what we have now. So there are additional challenges. Okay, technically this is something that we need right now, or something larger than 20. The picture I showed, everything is on a 2D plane. So the signal goes in single plane. However, when you have a lot more line, the signal needs to cross through, so it needs to go up and down. So you need to go beyond the 2D plane. So what we can do is, for example, we can have flip chip technology. So you have two chips bonded together, and the signal can go up and down. So you bond them together with indium bonds usually, and then you actually create a hole via through the silicon, and the signal, and this is lined with superconducting metal, and the signal can go up and down from the top surface and the bottom. So we are in collaboration with IME together with this both the indium bonds and the TSP. So ideally we want something like this. So maybe from the PCB it's already connected to the indium bonds, and then the chip and the flip chip are connected again with the indium bonds. We are slowly developing that together. This is kind of like the first test of flip chip that we did. This one doesn't have a TSP yet. And then, so this one, for single FPGA board that we use, requires, works for about 8 qubits. So if we need millions, then we need thousands of this board. So it's a lot more. However, the issue would be on the bridge side, because there is a limited space. So if we use this standard coaxial lines that we use, of course, it's a bridge manufacturer, it's from Cleveland, and the one that we have is already called the XL version. So it's about 2 meter high, there is about maybe about 1 meter. If we fill everything with the coaxial lines, that's about 200 lines. So that's about for 100 qubits. However, for example, like people are also developing this method using this cryoflex line that can pack everything together. For example, like the IBM's mouse all this. However, at some point, if you have too many lines, this actually becomes too much heat load. So I think there is a limit of like maybe about 1,000 lines inside the fridge. So what's next? Maybe we can make a larger fridge. So this, I think, IBM is developing something called GoldenEye, like a concept fridge, which is very large. You can see a person in there. I think Fermilab in the US is also trying to develop this. Or maybe you can link this together. So this is a cool experiment by Zurich, I think. So they connect these two fridges together, and in between this line is actually cryogenic, so it's still in the millikelvin temperature. So then they actually send microwave photons back and forth between fridges from one fridge to the other. But again, eventually that we need hundreds of thousands. You need several 10 or 100 fridges next to it together. And the gap between here may cause delay in the computation. So maybe we can do other things to try to minimize the number of lines going in and out of the fridge. So right now, because we have everything going from 300K down, maybe we can cut down the number of lines. So this is the idea that people have brought up. We will see how well this will work. So one would be we have this CMOS technology to send and receive signal and put them maybe at 4K. So people have tried for semiconductor qubits in the negative range. Maybe we can put something inside the milli-Kelvin stage, and there is something called RSFQ logic, rapid single flux quantum. So the information is stored as a magnetic field, and people have actually shown they can send like a control qubit in at 10 millikelvin using an RSFQ chip, the same chip. However, I show this demonstration is only for one qubit. If we control hundreds of qubits, we need a lot more of this, and the heat load might be concerning. So we have a collaboration with Professor Ali Bosde in Turkey, and I think right now we are thinking maybe this would be too much of a heat load for many qubit processor, and we are thinking of maybe putting it at the 4K stage. So I guess that's kind of the summary. I listed many of the challenges, and there will be many challenges. Before I finish, there is one slide I picked up from my friend Dr. Yapi Hussain at UTM, and when he found out I was going to this BRIN workshop, he sent me these slides. So he is part of this Malaysia Quantum Initiative, which is member from 7 universities. So Dr. Yap is the guy with force on the right, and I also know Dr. Thomas Patek, and they basically started this quantum initiative. I think they started last year and only have in person meeting this year. And maybe if you want collaboration with Malaysia, then contact me and I will forward them to you. Okay. Again, I know there are some development, but not much results.
If you increase the number of qubits, do you expect that the reality per qubit is big?
Yeah, so I mean, once the qubit is coupled to more and more qubits, I guess then that acts as an additional channel of loss. So also, like if we try to say measure the fidelity of two qubits at the same time while basically doing everything together, I do expect there will be some reduction. People I think have shown some of this, and I guess some of this kind of gates, basically like two qubit gates, show this can be minimized somewhat depending on the architecture and the sequence of the gates.
Ini agak dia kalau kita tahu sebenarnya kalau mau bikin dalam qubit kira-kira butuh berapa uang?
Oke, berapa ya? Kalau udah ada clean room, if there is a clean room with all the fabrication facilities, that helps a lot because you need basically photolithography machine, EV lithography machine, metal deposition, but that can be shared with other facilities. So dilution phase by itself, the Blueforce XL is about $1.5 million US dollars, and then all these like instruments are not cheap. Like the FPGA board is one board maybe is about a few $1,000. So 8 qubits, we just need one board, I guess. So yeah, I guess $3 million. That's not counting the applications parts.
For designing the qubit itself, I mean, electromagnetic simulation, the software is free or it is tightly controlled software, and also for the layout of the record, there is like a simulation for that. Is it free or also tightly controlled?
So for the drawing, I use like the free CAD software like Helio or whatever. For the simulations, typically they are not free. So ANSYS, we use two licenses. One is the high frequency, the HFSS license to simulate the frequencies of the resonators, and what's called Maxwell for the capacitor simulations. And I think those are each about, for academic license, about 2,000, 3,000 Sing dollar for annual license. So you have to pay this every year. The problem ANSYS has this
have a lot of people in undergraduate army who are also capable of doing simulation that we don't solve easily. Yeah, just for information, maybe if you want to collaborate with them, like you have some project that want to show to undergraduate for designing from BRIN, yeah.
Yeah, that would be nice. Yeah, none of us in our group have any cryogenic knowledge. Basically, we just have the fridge, press start, and it will cool on in 2 days. So yeah, it would be nice to, or like some kind of heat load simulation of like how many lines we can actually go inside the fridge. That would be something interesting.
Yeah, I mean, at least for general design of the fridge, right? Before order to the company, or maybe order to you.
Yeah, yeah. Okay. Okay, food is coming. Yes. Yes.
In your beginning part, I saw one of the one that was small, but then you find the cubic space and
So, okay. So n and n plus 1 Cooper pair. That's
what does it have to do with the modified oscillator?
so for transforms, I mean, I think this number of like Cooper pair is more to like the old charge qubits, that's called the Cooper pair box. I think that one we can actually define the quantum state is exactly n or n plus 1. But because of this modified, and I think the definition of charge and phase at this point is less clear, as only that you have like a some capacitor also. So I think this current modern like platforms that might be less clear, but it was derived from this what's called the Cooper variables. So like Cooper variables basically they have this restriction of E or C like that. Okay. Are there any more questions?
Stupid question. So, if we have a particular answer later, so we can have particular answer.
I mean, there is also the photonic qubits that work at room temperature. But I mean, so that's the question, right? Like earlier. So people have tried making YBCO qubits, and that seems they seem to have some difficulty. So even if we have like room temperature superconductor, now we need to figure out what would this aluminum aluminum oxide. So we cannot use aluminum junction anymore. So we need to figure out what would be a good dose junction for this kind of room temperature qubit, and that require more research, I guess. So I think once we have like room temperature superconductor, it's still going to be like I don't know, many years until we find room temperature fluids, and then maybe many years later we can build room temperature superconducting qubits. Okay.
Do you work other than developing qubits? You also work for designing how until you develop everything around the qubit themselves.
So these days I mostly work on like the design and junction fabrication. So we have other people that work on like the gates themselves, what kind of algorithm to use. So yeah, I don't know. I don't work with that much.
Okay. Maybe I also have a general question. We can talk about or technically related to I'm just thinking about how people actually control the gates to their code. I mean, is it that physically the gates can be constructed to do something on the qubit and then stay my way back and then go back to the gates. Physically,
So
by the code.
the gates, I mean, so there needs to be a translation between like these gates and the gates and the microwave process. And so for every qubit, basically at the beginning we need to do this characterization. So we need to find what kind of like good frequency, good gate duration, and those usually for this kind of quantum clouds of this, there is always going to be like this calibration process. I think IBM, because I mentioned a little bit about this qubit fluctuations, right? So you actually have to do this calibration every time. So I think IBM actually does this twice a day or something. Okay, I think we have to close the sessions, and thanks again to Dr. Rangga. And now, since our clocks are ready, we can go lunch. The next session we will start I think around 2:15, and the next session will be moderated with Dr. Rangga. So now is lunch.
Oh iya.
yang kayak gitu biar bisa nelen no.
Makan tuh.
Good afternoon, everyone. Maybe the afternoon session will be shortly. Please then we will start the next session. Can we start the next session? Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. And next up, the afternoon session. This is software Pennylane, just mentioned before by Dr. Galus. It can be used for simulating the quantum chemistry system, and it is hands-on. Mr. Yusrul will show how to simulate maybe hydrogen molecule and also making hydrogen molecule and solving by Arizona tools using Pennylane. And if you want to try this hands-on or tutorial, please using your laptop, and Mr. Yusrul can guide you how to simulate the system. And all of the materials is already given in the website, and you can download the materials on, or also you can go to the GitHub. Mr. Yusrul GitHub, and just like tomorrow session. Jadi, Mr. Yusrul, you can start the exercise session. Maybe around 1 hour. Please.
Okay, thank you, Dr. Edi. Good afternoon, everyone. I think, yes, your face is very happy because you have a lunch. Okay, before we start to simulate with the Pennylane, I will give you some information about, yes, in yesterday, some participants have trouble with simulating with the discrete values. So there are so many, not only participant, also me. Okay. So this one is because yes, I have mentioned before that this kit have some package integration, like some, yes, some package mixing, or some package appear. So this configuration have changed a lot based on the previous my method. So please go to my GitHub again, so you can learn with my GitHub first, especially in introduction. So this code I have revisit in morning because so many complain with me. Okay, my calculation not working. Okay, so I think this code running is very good and very clearly until the end. So there are so many configuration like this, how to show the, sorry, how to visualize this quantum circuit, and also how to, maybe this one is very this one is very, maybe it's a lot of error in this part. So this one I have modified. So this participant could determine the unitary transformation from arbitrary state. So okay, please, you can download this my GitHub. Okay. So I moved into how to simulate quantum chemistry with Pennylane using the experiment that after taught by Dr. Agus that give me some explanation about Pennylane quantum chemistry. So the Pennylane quantum chemistry based on the TQA, the variational quantum Hacking solver, That means that you have to some answers like the initial state or initial case of the twin calculation. So and then after that, this simulation doing some machine learning to predict some local minima of the energy of the system. Okay. So before we start, please install Pennylane Fusion. Okay, because I have already so this is already already this slide, and then with this recommendation. So, yeah, long way learning. Okay, so the first one is how to simulate hydrogen molecule. So the Pennylane library is based on quantum computing and also is so they have to the goal of this simulation to determine the this is a very important one. So the molecular and representative type that spin. So what that means that hydrogen have the one electron. That means that we have configuration spin up and spin down. So to doing calculation, we have to number of qubits as equal to 4. Okay, continue. So this means that when you simulate hydrogen molecule, you have to number of qubit equal to 4. This means that represented by spin up and spin down every configuration of the hydrogen electrons. So this means that when you print the Hamiltonian list, so you can see that the Hamiltonian representative by this in the C2 is mean Z get in the qubit tree, so the value of minus 0.242 is mean that coefficient of the probabilistic system. This is a configuration to construct of the Hamiltonian from the hydrogen molecule. Okay. So what about how to generate a vector via the hard default state? This means that I have mentioned earlier that in the Pennylane you have to define some answers. Answers means that you unknown function to give some initial state from the state. So this is a crucial part to the determine of the some simulation of the system and the behavior of the system. In this part, we assume that we using hard default state to simulate to determine the hydrogen molecule current state. In the first one we can use device how to utilize. This means that there are many there are many devices and you use in the Pennylane. There are some default qubit, default mix, Gaussian, lightning qubit, and lightning qubit. There's five devices have the different configuration. You have yesterday. But in this tutorial, I try to use a default qubit, but after in home, maybe a participant could using lightning qubit. What is different with the two results? So this one is I'm using default qubit, and why is how many qubit I have to define? So this is equal to qubit because the hydrogen needs number of qubit as scale 4. So I have mentioned again, and then we have to define some number of electrons. So hydrogen has the electron configuration is equal to 1 or 1s, and then because hydrogen molecule have two atoms, so we multiply it, and then hydrogen molecule have atom two, and then we try to generalize, to generate some answers through the IF state, default state, as in this one, and we printed what the means of default state. So this means that 1100. What it does mean? 11. This means that the electron are occupied, and the 0 this means unoccupied. So we have for the spin configuration. So this one spin have occupied, and the third and fourth and unoccupied. So representation of the Hartley-Fock state follow the Jordan with the representation of state like this. So if you maybe Dr. Bagus can explain to you, but maybe you maybe in my opinion you don't understand how the meaning of this. Okay. So okay. In the Pennylane, we have to represent the Hartley-Fock state with a certain representative state. There are three configuration: reference, single excitation, and double excitation. And in the reference, this one is spin up. This blue color is spin down. This means that in configuration in the cubic one. So the first one is 1, 1. This means that in a cubic 1 of 5. Okay. So this means that 1, 1 is represented by occupied. But in the cubic 2, you can see it that cubic 2 is mean 0, 0. This means there is no configuration spin in here. Okay. And cubic 3. So this when you can understand it. We can move a single excitation. Okay. And the single excitation, the spinner moves to qubit 2. This means that in qubit 1 only configuration is spin up and 0. This means there is non-occupied in the qubit 1. But in the qubit 2, spin up doesn't move, so we can write with the 0 unoccupied, and in the qubit 2 spin down, so we are occupied. So this 1, 0, 0, 1, 0, 0. Okay. So double excitation. Okay, maybe in explanation as explained before, we spin up move, so there is no occupied state in the qubit 1. So 0, 0, okay, 0, 0. And when I spin up to move the qubit 2, so, and then there is no spin down, so occupied only 1, so 0, 0, 1, 0, and qubit 3 and 0, 1. So this means that representative of the third nuclear state to analyze Hartley-Fock state. Okay. Maybe to analyze the construct of the circuit based on the Hartley-Fock state using some derivation function of Python. Okay. So, four. Yes. This means this representation only give some insight what is meant or what it has mean of the how to set this reference, single excitation, and double excitation. When we are dealing with the qubit 4, so maybe some participant can put some qubit in the box. So
These are only 3 among many.
yes, yes. Okay. This is only a general explanation. to represent with the GDP. So we have to construct the initial circuit based on the answers, because answers yes, we are uh, we have to call it, and the widest equals widest is number of qubit, and then in here we apply the double excitation operation. So the first and until for qubit, so we have to define 0, 1, 2, 3 years. I have mentioned in yesterday that Python indexes start with the zero. Okay. So after we have dealing with and declare some answers to construct some circuit. So how to we dealing with some cost function to compute the expectation value of the Hamiltonian molecular in the trial state based on the Hartree-Fock state. So maybe the cost function is you can follow. This is decorator. In Python you can use it. This decorator has mean that maybe to call some hidden function in the hidden function providing the Pennylane package. So that cost function is we need to find the sum of cost function to determine the expectation value of Hamiltonian based on the molecular. So after we construct a survey, we have to do the Hamiltonian. So this one is showing how to calculate the local minima of energy of the hydrogen molecule. In this tutorial, I'm using the gradient descent optimizer. So this is when you are familiar with the quantum, machine learning. Yes, this is your favorite part. When you first study about machine learning. Okay, there are so many optimization, not only gradient descent optimizer. I use Evan. So, but maybe the give you first insight that in this tutorial I'm using gradient descent of in step of the discretization of the determinant local energy. So maybe also we initially to start with the 0, 0 data, okay, and then we carry out how to optimization of the function, of cost function, and also to determine some let's say that current state energy from the Hamiltonian of the hydrogen molecule. So in here the maximum step is only in 100 step, but in the different system, maybe we have to define more steps, maybe 1,000 and one when we depends on the system you define. So the reaching a convergence tolerance, we 10 powers of -6 for the value. This means how to calculate. So this means that we optimize of the quantum mission learning using a gradient descent optimizer, and we initialize the list or the cost function to win the energy list, and then we go to we have to call the data, because data in start with the 0, 0 maximum iteration we have given the 100 and confidence threshold with this one. Okay, this one is a very looping the things, the key of the optimization. So the first one is we have to with initially with a cost function and data because data is assumed 0, 0. So 0 means and we have to do some step and cost calculation, and we have obtained some energy from the calculation list to into the list, and also we generate the new angle of the optimization. So after that we compare with the previous previous result of the energy with the new energy. So that means that this energy is matched with the configuration threshold we have declared. So calculation may be with smooth and done. So optimization if you parameter if you declare is so the other step and up to 12. So this means that in the configuration threshold we have declared. So the calculation maybe 2 million until maximum 100. So because but we have until step the 13. So we have got some energy current state of the Hamiltonian molecular as before. This means that the unit energy is represented by heartbeat, not in EG. And then optimal value data shown in the 0.2089. So what about how do we compare with the realistic result? So this means that full configuration interaction of the hydrogen this one. So you can see that the energy of the constant energy of the molecular hydrogen molecular close to the experiment result of the XGI. There's something energy match because we have done the initial state and give some sampling with the hard fork. So this one is the result agreeing with the experiment result. Okay. Any question?
If you use the actual quantum computer, you then have to measurement time the quantum energy. That means that's a conversion. That's a conversion, yes. So you have to make as many measurements as you need to do.
Yes. But yes, of course, this is challenging. After that, yeah, we know that hydrogen is a simple one to simulate. But in the lithium hydrogen, we have some problem. We have some problem to do when we to find more qubit, we have more sampling like maximum iteration and also the convergent threshold you have to maybe I have mentioned. So but there are some other method to doing with it. Not only some in the qubit, but we have limit some setting like electron configuration and also molecular. So this, maybe the next one is we have to calculate with a different configuration to determine ground state energy. So okay, maybe this one. Okay. In the previous quantum chemistry model, but the quantum Hamiltonian, if you maybe I jump into previous. So in model Hamiltonian only depends on the symbols and coordinate. Okay. So I think we have a maybe yeah we have a big okay in this chemical and theory. So I have maybe I have a positive thinking. Okay, this calculation and doing any computer, but in the complex system, it's not doing more configuration of qubit. Okay, so maybe I
Can we get the explanation of how we obtain the expression of the Hamiltonian?
okay. Maybe okay. So I copy in the lithium hydrogen first. What happened? What happened? We doing uh, some working on the hydrogen molecule with the determine this lithium hydrogen. How many qubit you have you have to utilize? Okay, so we need 12 qubit. So 12 qubit I think is I think more complex to doing calculation. And then when we okay, there are so many configuration of the gates. Okay. So I think it's not a single way to declare with it. So okay, maybe
How do you come up with the requirement for that?
I think it's really more time consuming computing using my local.
There's some minimum number to the number of electrons.
Yeah. That, in this one, I'm using that of the lithium hydrogen electron, assume all of it, assume all of it with the active electron 2, but in the configuration of spin up and spin down, we have 12, 12. So with the configuration spin up and spin down up to 12, we need equal to number of qubit equal to 12.
Yep, yep. 3 plus 1 electron.
Yes,
More electron.
yes, for electron. But in a Pennylane, they assume that we have the configuration spin up and spin down. Not only we have the wave 3 electron, depend only the 3 electron, but we have to multiply with the spin up, spin down. So this is a very challenging.
Since we have to count the number of artifact states, which is number of electrons we have, then from there, we figure out how many AC states that we need, and that way we can calculate how many qubits. So I'm just wondering why we come up with 12.
So yes, because you believe in the system, okay, maybe I don't worry about the computers or we believe in the computer and so on. It's just I think not quite smart to do similar to it. So in this tutorial, we have a different method. We only active electrons swimming with 2 electrons. Meaning lithium and hydrogen have the electron configuration in one arm. So we have to do that first. So we have to more. When 12 electron is spin down, we string it into active electron only the 2 electron, and also active orbitals which remains only 5 molecular orbital. So what happened is maybe I have to understand. Okay. So we all know that to calculate the lithium hydrogen molecule, we need number of qubit until 12. What happened? We limit only the active electron only 2 and active orbital only 5. So what happened? Okay, we have to declare some. This means that we not using configuration of the qubit again. So, but we represented by the number of excitation value of the system. So, and then we try to optimize. I have mentioned before that the Pennylane have the trouble with the initial state. So we are doing wrong in the decline initial state. You have maybe you have a wrong result, and also when the time consuming you have to avoid it. So maybe in this calculation we come up with the single excitation and double excitation. We we sum it, and then we declare again in the hydrophilic state only configure the active electrons. Okay, this qubit means that this qubit and default from this one. Okay, so we are doing some way. Okay. But in the hydrogen molecule, we are using distant optimization. But in the day, we are trying to choose another optimization with adaptive optimization. This method has explained with Dr. Rangga in the morning. So what happened? But in this tutorial, in the gradients only I have convergent threshold only with a minimum value is 1. So after this energy have to meet lower than the convergent threshold, so operation have to break. Maybe it's long enough in the hydrogen. Okay. So in the Pennylane, when you try to visualize the kit is not fancy. Only give you some line like this line fancy with the compared with the biscuit. They will long enough to waiting for the this is only configured with the limitation of the electron. Maybe any question? Question? Waiting for the calculation.
So, let me ask
I don't know how to. I don't jump into specific topics, how to define concept and coping
I
parameters.
think the question lies in how activity contract the method. Is it type binding type or the original actual method?
So, because Pennylane based on the variational quantum mechanics solver, that's been that we
There's a
design.
method to solve it, but first of all, the method, yes, what of the method to solve it?
Yes, to define some gates in the circuit, we have to sampling the gates to match with the Hamiltonian. So this one is we are using some maybe some machine learning to doing a job with matching with the Hamiltonian. You have matched with the okay. I have a system with Hamilton like this. So maybe the chemical using machine learning to find how to get the configuration to match with the Hamiltonian match. So this is challenging. Maybe I have explained before that you have wrong with the initial state, you have wrong the result, and long enough to doing the result. So we have yes we have to be smart in this calculation. Okay, and it's calculation done. What happened? Okay. Okay. You have seen that the optimization I have mentioned in cut until the until maybe six optimization state because this calculation have stop because result I have a calculation result. With the experiment result, you can change with this convergent threshold with the maybe with the hydrogen this convergent threshold in hydrogen. But I do not do it because yes, long enough to waiting. So with the calculation, but if you try by yourself, so please some maybe some sampling with the confidence ratio and anything else to get some insight how to sampling with the Hamiltonian. So maybe if you have a question, how to define some graphing? When you define graphing, I and the total values have a similar problem with the maybe the one computer resource and also the time. So because we have to dealing with the initial state, so we have to face off. So calculating and graphing is not simple like we define some technical parameters. Maybe any question, but not only limit by this talk. Maybe the previous talk you can ask me. the question from me. Why will the graphene is soluble? I think you just to define atomic symbol and position. Yes, yes. Yes, yes. The difficulty is not only depends on its equality and also atomic position of the graphene. The the challenge is the number of the electron input of the calculation. So if we input calculation of the graphene, we have to configuration of it as PC or B, like in the type writing, but in the chemistry, electron configuration SP2. So we need more SP2 is for electron, for electron have the spin up, spin down. Yeah, the Pennylane is good for molecule because graphene is the crystal in structure. Yes, begitu. I gave you information that Pennylane is the good enough when you are doing a molecular organic study. So because the crystalline, we need define some maybe so we need selective repetition. So maybe this method not give you very fast practice. So this maybe the fitting with your molecular material like hydrogen, carbon dioxide, and also lithium dioxide. Maybe so on you have to. Okay, still any question from the audience? No problem. If you tomorrow, yeah, will be
Yeah, I have a question, Mr. Yusrul. Uh, is it possible to calculate on ionic system because I'm using biscuit, the system doesn't know is it ionic or less charge or another charge. And I also tried in Pennylane, the hemoglobin is the same between the ionic and the normal. Is it possible that we can change it so the hemoglobin is different? Okay.
okay. Thank you for the question. I think I can give you answer very certainly. So yes, maybe the first one, and I can say that I don't know. I don't know because yeah, I'm still new in the Pennylane, so I'm still new in Pennylane, so I and Dr. Bagus study together how to simulate some automated molecular and ionic. So we have to sampling to get some optimization of the system. So yeah, the first the thing I can say I don't know. Yes, maybe simplify to say that yes, we can define some part of it, but after the calculation, yes, the machine learning to predict some Hamiltonian level count. So we face after some okay, simple okay. I have this one okay because some steps on this, but when to the hard form as answers and then doing some optimization, we have a problem with it. Some the okay maybe your calculation only your computer, maybe your computer maybe you have on this thing. So we don't know because yes we only maybe I can say that it's not simply that you see.
Okay, question? No, thank you,
say. Okay, thank you. Next question, please.
Thank you. I want to, when I search the Pennylane web, they have Phoenix data set. So when I read it is actually image data set means then they convert to quantum physics and then using machine learning to learn the data set. So I wonder if we have a real world data set, can we use also Pennylane machine learning to influence the prediction or classification using this machine learning, not limited only on like quantum world, but also in like the trade data set or non-data set. When I see this, they using image data set to classification and they use image. They convert it to quantum physics. If you have any experience with that, and if you have, can you give step by step of implementing the thing?
Okay, thank you for the interesting question, and maybe if we encourage to learning more about how to learn with data. Yes, and Pennylane, maybe had mentioned by Dr. Gibbs that at the not limited only this calculation. We are dealing with some supercell and these are more bigger than hydrogen molecule. We in Pennylane also some first of the data of how to construct the Hamiltonian. So yeah, maybe the first one is as far as I know that Pennylane doing machine learning with advanced data on, but yeah, if you want to contribute with the data, you can maybe have a request in the GitHub access, so you can maybe contribute with the community of Pennylanes, how to find some the new Hamiltonian. But yeah, as far as I know, I could say that. So I can give you some how to deal with it. So because yeah, I'm still learning how to expand more, not only limited by the determine the current and current state energy. Okay. That is the question. Ini simple question, Mr. Yusrul, just like this kid, yesterday, can we use the quantum computer to run the simulation or? Okay. Okay. So for information, we especially we could calculate this Pennylane with the quantum computing with the SANADU. But I mean, there is we cannot access maybe in the maintenance or anything else. We don't know. But yeah, in previous way, there's Sanadu, one of the maybe platform to that expanding the to create some upgrade of Pennylane and give you access. But in the day, Sanadu close the computer to connect with your local computer with the Sanadu quantum computing. Okay. How this is there any question? Yeah, that's question from Francis.
Besides the graphics, do you also do calculations for the
Yes, in the Pennylane have I wonder how to find some excitation, right? But yes, in Pennylane we can do some calculation with excitation state. So I forgot how to what model can use it. Maybe if no more question, we thanks to Mr. Yusrul for the hands-on. Thank you very much. And the maybe today agenda is already finished, but tomorrow we still have one workshop start from 8:30 by Dominic from IES. And also we have real quantum computer will bring to this group tomorrow by company that is a steam cube. So if the visit, if you want to see how the quantum computer works, and they will demonstrate the steam cubes from interface of quantum computer. So see you tomorrow, and thank you very much for the attention, and we close the today workshop. See you tomorrow. Thank you.